Hi everybody, in this module we're going to talk about some of the properties of atomic nuclei. Before we talk about atomic nuclei in more depth, it would be helpful if we could find a set of units that is convenient to deal with. In particular, in nuclear physics, we are dealing with particles that have very, very small charges, very, very small amounts of energy, and very small masses compared to human scale objects. So our SI units, the coulomb, the joule, the kilogram, they require us to do calculations with these awkward factors of 10 to the negative 19 or 10 to the negative 31. So we would like some units that are a little bit more suited for the scale that we're working on. A nice unit for charge at the particle and nuclear physics scale is just using the charge of the electron as our basic unit of charge. We've already seen this a few times in units 2 and 3, where instead of giving charge in coulombs, we gave it in some multiple of the charge of an electron. So 1e equals 1.6 times 10 to the negative 19th coulombs. In nuclear units of charge, the electron has a charge of minus 1e, and the proton has a charge of plus 1e. And that way every nucleus or atom has a nice integer value of charge. Hopefully you can see that having a nice integer value of charge to work with is much easier to immediately understand if I say the copper nucleus has a charge of plus 29e than it is if I say the copper nucleus has a charge of 4.64 times 10 to the negative 18th coulombs. Now let's talk about a convenient unit for energy at nuclear scales. It would be nice if we could have a unit of energy that is also directly related to the electron. If you look up the SI unit, the joule, on Wikipedia or some other open source, you can see that one of the ways to express energy is just volts times coulombs. This works really well for us because we can already translate coulombs into our new convenient nuclear unit of 1e. So we can build a convenient unit of energy by just saying that the charge of an electron times 1 volt is equal to 1.6 times 10 to the negative 19th joules. This new unit of energy that we are using is called an electron volt, or just EV. So now we have our unit of energy, the electron volt, equal to 1.6 times 10 to the negative 19th joules. Let's think about what this means. 1 volt times 1e is equal to the energy of an electron when it is placed at a potential of 1 volt. So imagine we are looking at an electric potential around a positive charge. This charge has lines of equipotential encircling it. One of these lines of equipotential will represent a potential of 1 volt. You might remember from Unit 2 that electric potential or voltage is given by V equals kQ over R. In this case, 1 volt equals Coulomb's constant K times the positive charge divided by the radius. Now let's go ahead and place an electron on that equipotential line. How much potential energy does it have? Well, we also learned in Unit 2 that electric potential energy is just U equals KQQ over R. We already know that the KQ over R part is equal to 1 volt. So that means that U electric just equals 1 volt times the charge of the electron, that second Q up there, or 1 volt times 1.6 times 10 to the negative 19th coulombs. If the electron is released, it would start accelerating towards the positive charge. And at the moment when it hits the positive charge, its potential energy will be turned into 1 electron volt of kinetic energy. The energy of an electron in the ground state of a hydrogen atom is negative 13.6 electron volts. We will talk about why this energy is negative a little bit later. Finally, let's talk about units of mass at nuclear scales. In module M5.1, we mentioned that nuclear and particle physicists like to use masses that are in terms of energy, according to the equation E equals mc squared, so that it is easier to take relativistic effects into account later. So one way to measure mass on the nuclear or particle scale is to take the amount of energy that would be created if all the mass was turned into energy, and then divide that by c squared, and that gives you the mass. Since c squared is a pretty big number, the energy that would be created is usually a much bigger number than the mass, so the number on top of the fraction is usually pretty big. Most masses on the nuclear scale are measured in mega electron volts, or MeV, over c squared. The mass of an electron is 0.511 MeV over c squared. The mass of a proton is about 938 MeV over c squared, almost 2,000 times as heavy as an electron. A lot of times, nuclear and particle physicists get lazy and don't bother saying over c squared. So I want to apologize in advance if I say that the mass of something is just MeV. The over c squared part is definitely supposed to be there if I'm talking about mass, I promise. If you are wondering why the proton and neutron masses are so much bigger than the electron mass, it is actually because the proton and neutron are not fundamental particles. They contain a chaotic soup of many quarks and gluons. But even then, the mass of the up and down quarks and the masses of all the individual quarks in this quark soup are only a few MeV over c squared, and the gluons are massless. It turns out that the majority of what we measure as the mass of the proton actually comes from the energy of all these quarks and gluons flying around inside the proton, smashing into each other, annihilating, and creating new pairs constantly at very high speeds. Since E equals mc squared, we at the human scale measure all of this bottled up energy as mass. I think that's pretty cool to realize that you and everything around you is actually made up of octillions of examples of Einstein's famous equation in action. By the way, an octillion is 10 to the 27th, so there are about 10 to the 28th protons and neutrons in the human body, give or take a few octillion. There is one more unit that is used a whole lot in nuclear physics. It is actually another unit of mass. We saw that it is very convenient to just use the charge of an electron as our standard nuclear unit of charge, so that we can say the charge of a copper nucleus is just plus 29e, instead of having to multiply everything by that awkward 1.6 times 10 to the negative 19th. Similarly, it would be pretty convenient to have a unit of mass that is directly relatable to one of the components of the nucleus, the protons or the neutrons. Unfortunately, the proton and the neutron have slightly different masses, so using one or the other would be a bit misleading. The solution that nuclear physicists and their close relatives, the nuclear chemists, came up with is to take a sort of average mass between protons and neutrons. So they defined the atomic mass unit, or AMU, to be 1/12 of the mass of a carbon-12 nucleus. Since carbon-12 has 6 protons and 6 neutrons, it should give a reasonably fair balance between the masses of the constituent protons and the masses of the constituent neutrons. You might notice that both the proton and the neutron have a mass that is a little bit bigger than 1 AMU. How is this possible if the AMU is supposed to represent a sort of average mass of the neutrons and protons in the atom? Well, this is because at nuclear levels, the energy of the nucleus also contributes to its mass. So when we measure the mass of a carbon-12 atom, we don't get just the mass of the 6 protons and 6 neutrons that make it up. We get another small contribution that represents the energy required to hold all those protons and neutrons together. But before we talk about this, let's go back for just a minute and talk about why the energy of an electron in the ground state of a hydrogen atom is negative. Way back in Physics 1510, you learned about gravitational potential energy. You probably learned to use the formula U equals mgh, where h was the height of an object from the ground. Using this formula assumes that the gravitational potential energy at ground level is 0. That is, if the ball is placed at ground level, it has 0 potential energy. But what if you dug a big hole next to this building and pushed the ball off of the other side? Does its potential energy change since it falls a greater distance? No, that doesn't make any sense. The ball should have the same amount of potential energy when it's sitting on that roof, regardless of which direction you push it off, regardless of how deep of a hole it falls into at some later time. What has happened here is that when the ball falls from the roof, it loses potential energy. When it reaches the level of the surface of the Earth, which we have defined here as the 0 point for potential energy, it does have 0 potential energy for a moment, but then it keeps going past the 0. So when it comes to rest at the bottom of the hole, the only thing we can say is that it must have negative potential energy. You can see that conservation of energy is still maintained because as it passes the level of the ground, it keeps gaining kinetic energy and it keeps losing potential energy. So total mechanical energy is still conserved. The situation is a little more complicated when we talk about electric potential energy because there's not a clear 0 point for any given problem, such as the surface of the Earth when you're talking about mass. If you look at the equation for electrical potential energy between just 2 charges, U electric equals KQQ over R, you will see that when the distance between the 2 charges gets close to 0, the potential energy is something divided by 0, which mathematically is defined as being infinite. The only time you can get a potential energy of 0 is when two charges are infinitely far apart. So the 0 point for electric potential energy is sometimes set at a distance of infinity. But if you set the 0 point for electric potential energy to infinity, that also makes the electric potential become infinite when charges are very close, and that can be very inconvenient as well. So the 0 point of electrical potential energy is usually defined in whatever way is convenient for a specific problem, meaning that there is really no definite way electrical potential energy is always defined. So electrical potential energy at a given point can be negative or positive, depending on what the question asks for and what that particular person solving the problem sets as their 0 point for electric potential energy. Luckily, when we talk about nuclei and atoms, there is a very clear point that can almost always be defined as the 0 point of nuclear potential energy, the point at which the particles just barely become bound to each other. You could think of this point as the surface of a sphere around the atom. Anything outside the sphere is not bound, and anything inside the sphere is trapped or bound within the atom. So just like the surface of the Earth, we give particles a positive potential energy when they are outside the binding radius. We say they are unbound or free particles. And when they are inside the binding radius, their potential energy is negative, just like the ball that fell into a hole and is trapped inside. Right at the boundary, the potential energy of the particle is 0. So this is why the energy of an electron, which is trapped at the lowest energy level of a hydrogen atom, called the ground state, has a negative potential energy of negative 13.6 electron volts. At the next energy level, a little bit further away from the nucleus, the electron has a potential energy of negative 3.4 electron volts and is a little bit less tightly bound. Since the potential energy is negative, that means that the energy required to keep the electron in the bound state must be positive. The protons and neutrons are bound even more tightly to the nucleus, since they experience the strong force holding them together. But the idea is similar. Each proton and neutron also has a negative potential energy. The amount of energy required to hold the nucleus together is the nuclear binding energy. And just like electron binding energies, if the nucleus is staying together, this binding energy has to be positive. Where does the binding energy come from? Well, it is tapped away from the chaotic soup of energy within each proton and each neutron. So in order for a nucleus to stick together, some of the mass of the protons and neutrons is converted into binding energy. We can now calculate the mass of a nucleus using the mass of all of its protons plus the mass of all of its neutrons minus the amount of mass that has to be converted into binding energy. Remember that Z is the atomic number and represents the number of protons, and N is the number of neutrons. Since we are subtracting an amount of mass equal to the binding energy, we have to use E equals mc squared and subtract a mass in the amount of the binding energy over c squared. More often than not, we have some means to measure the mass of the atom in total, and what we actually want to try to find is the binding energy. So we can just rearrange the equation to find the binding energy. I know that a lot of you feel more comfortable with numbers and you like to plug in values as soon as possible, but I want to strongly encourage you to leave that c squared alone. Don't plug in the value for c unless you absolutely have to, because once you translate masses into EV over c squared, all the c's usually cancel, leaving you a much smaller chance of calculator error. Let's see how this works by finding the binding energy of copper. In particular, let's look at copper-63, the most common stable isotope of copper. First, we know that copper-63 has 63 nucleons and that copper has 29 protons. This means that copper-63 has A minus Z neutrons, or 63 minus 29 equals 34 neutrons. Now, the atomic weight for copper that you see on a periodic table of elements is an average of the mass of all the isotopes. We need a mass of a specific isotope, copper-63. You can probably find this online pretty easily, but I will just tell you that we will use an atomic weight of 62.9295975 U, or atomic mass units. So we can plug all of these values into the equation, leaving the c squared exactly as it is. I like to add the protons and neutrons first. You can see that this number should be very close to the mass of the atom. So this is a nice check to make sure you did the math right so far. Now here's the trick to get rid of the c squared. We want to find the binding energy in our nuclear units of energy, MeV. So now we convert from atomic mass units to MeV over c squared. We end up with 551.3862 MeV over c squared, and then that whole quantity is multiplied times c squared. So all the c's cancel as promised, and we end up with a binding energy of just 551.3862 MeV. One very important thing to realize about nuclear physics calculations is that rounding numbers too early can be disastrous. Let's do that calculation again, but instead let's round everything to a more convenient number of digits. We end up with a binding energy of 568.2 mega electron volts, which is not considered accurate enough for good nuclear physics. And perhaps more importantly to you, this is outside of WebAssign's industry standard error of 2%. This is because, as I mentioned before, c squared is a pretty big number. It's 9 times 10 to the 16th. So when we're converting a mass into energy with this very large conversion factor, even the tiniest bit of error gets magnified by quite a lot. I strongly recommend that you keep the same number of digits that you are given in the problem all the way to the end. So since the mass of the proton and neutron are given with 7 digits and 6 decimal places, I wouldn't round to anything less than 7 digits until you have your final answer. There is one more important thing about nuclear binding energy. It is useful to compare the relative binding strength between different types of nuclei. But to do this, you really have to consider binding energy per nucleon instead of just straight binding energy. So oftentimes, when nuclear physicists or nuclear chemists talk about nuclear binding energy, they actually want to know the nuclear binding energy per nucleon, or Be over A. So the binding energy per nucleon of copper-63 is 551.3862 divided by 63, which equals 8.7521 MeV. Again, nuclear physicists sometimes get lazy, and they refer to this just as the binding energy, which can potentially be confusing. So if you try to look up binding energies online and they seem awfully small, you are probably looking at a binding energy per nucleon, not the full binding energy. You can see that the atoms with the highest binding energy per nucleon are isotopes with around 56 nucleons. A high binding energy per nucleon is associated with higher stability because there is more energy holding the nucleus together. The isotope with the highest binding energy is actually nickel-62, with a binding energy of 8.7945 MeV per nucleon. Iron-56 has a binding energy per nucleon of 8.7903 MeV, which is slightly less, but it has the lowest mass per nucleon and is therefore the most stable isotope in the periodic table. Let's finish this module off with one more property of atomic nuclei. Don't worry, this one is pretty easy. We talked about how in larger nuclei, the protons and the neutrons on the far outside of a nucleus are too far away from the nucleons on the other side of the nucleus to feel a whole lot of the strong force attraction. We have also talked about how the 0 point of the potential energy of the neutrons and protons is measured from some sphere surrounding them that determines when the nucleus is bound and when it'll start falling apart. In both cases, the radius of the nucleus becomes an important quantity. The formula for the radius of a nucleus is pretty simple. It is just the cubed root of the number of nucleons times a constant, R0. Since a hydrogen atom has just a single proton, A for a hydrogen atom is just 1. So the cube root of 1 is just 1 again, and you can see that R0 is just the radius of a hydrogen atom, the smallest nucleus. Make sure that you know how to do a cube root on your calculator. We saw that the most stable nuclei have about 60 nucleons. The cube root of 60 is about 3.9, so the most stable nuclei have a radius of about 4.7 femtometers. This is about the limit of the strong force, which has a range of about a femtometer. After this point, the electromagnetic repulsion of the protons starts to be stronger than the strong force attraction, so nuclei are less stable. So in this module, we talked about some of the basic properties of nuclei. First, we found some units that are convenient to use for nuclear physics: the electron volt for energy, the charge of an electron for charge, the atomic mass unit, U or AMU for mass. And then we also saw that using energy over c squared, or MeV over c squared, as a unit of mass makes it easier to navigate the relativistic relationship between mass and energy, E equals mc squared, that is commonly found at the nuclear scale. We learned that the mass of the nucleus is the total mass of all of the protons and neutrons minus the binding energy required to hold them together. The nuclear binding energy is also quoted as binding energy per nucleon, or Be over A. The radius of the nucleus is R equals R naught A to the 1/3, where R naught is just the radius of the hydrogen nucleus.